Hi, my name is Alex Krenzel, and I'm excited to be presenting this work on behalf of my collaborators at Google, UC Berkeley, and Cornell. Now, in this room, we're all very well aware of the importance that global WANs play in enabling planet-scale computing. But beyond this room, this becomes perfectly clear when network outages occur, as they have a huge impact on cloud providers and their customers. These outages continue to occur despite decades of experience and best practice operating and building large-scale WANs. And while some smaller outages are to be expected, the continued existence of medium and large outages is perhaps more concerning and even surprising. Now, I wish I could tell you the categories of common root causes for these outages, but the reality is that these large outages often are root caused by complex and unexpected interactions between multiple components and are rarely due to the loops, dead ends, link cuts, and protocol bugs that we as a community are equipped and have the tools to deal with. As an example, I present an outage that occurred at Google in which the dedicated edge clusters that run the SDN controller jobs had a slightly buggy configuration push. And months later, during a maintenance operation, a typo triggered such a bug that killed a number of the SDN controller jobs for a portion of the network, resulting in traffic falling back to the shortest path and leading to severe congestion. Now, it's not this specific bug that's important here. Rather, it's that each of the large outages is some complicated combination of problems like this one that doesn't generalize to a single type. Therefore, in this work, we ask the question, what can we do at design time to try to limit the occurrence of such failures? Now, network designers today have already developed some techniques to help, including isolation to limit blast radius, ensuring there's diverse redundant components, and applying formal verification to try to guarantee correct behavior. However, no existing approach is comprehensive, as global scale WANs are just incredibly complex. Therefore, we take an orthogonal approach in our work of aiming for simplification of our network to try to decrease the space of possible failures. More concretely, we ask, are there components of our WAN networks that we can take out while improving or at least maintaining functionality, performance, and cost? This covers our problem statement and motivation, and through the rest of this talk, I will first cover what SDN WAN architectures look like today, then discuss the opportunities for simplification that we see, how we take advantage of them in creating our approach, Decentralized SDN or DSDN, and finally cover some performance evaluation. The SDN WAN architectures of today are born of a world of protocol-based WAN architectures of the past. Now, decades of using these protocols showed that they were very survivable, providing some amount of resiliency due to being distributed, but were difficult to evolve, to add features, and complex and inefficient due to the consensus required for convergence. And so thus, over the past 15 years, large-scale WANs have shifted to SDN-based architectures, in which a central control program written by the network operator collects a global view of the network, computes paths, and programs them back into the network. However, this conceptually simple view is, in reality, more complex for large-scale WANs. These WANs that span the globe actually, in reality, have some sort of hierarchy to their control to provide aggregation. These hierarchical control jobs and the central controller job run on a network operating system that requires running on dedicated hardware in data centers across the world. For these control jobs to reach the routers, this requires a control plane network that additionally provides connectivity between the control jobs themselves. And finally, to produce and provide the inputs necessary to the controller requires dedicated demand and topology services. Now, in case of any failure in this complicated diagram, we may result in a split brain scenario and therefore continue to run old protocols as fallback. So in summary, there's a whole host of new and external dependencies that come with SDN WANs today. And actually, we continue to maintain the same old undesirable dependencies of distributed protocols of the old world. And this complexity is indeed reflected in the outages that we see, as it directly translates to increased surface area for bugs. Of the largest 41 outages over the past few years in our SDN-based WAN at Google, we find over half to have a root cause in the control plane or control plane infrastructure. We aim to tackle these outages by taking on this class of complexity root cause directly by aiming for simplification. But this cannot be done by simply going back to the distributed protocols of the past, because SDN has given us benefits that we've come to rely on. These are namely, one, being able to run operator-defined code, which enabled custom and superior implementations. Two, being able to run optimized TE computations based on a global view of network state. And three, the simplicity of consensus-free path selection that came with having a single central controller. So our goal is to simplify while retaining these benefits. And to do this, we see a way forward through recent router ecosystem developments. So first, over the past few years, we've seen that routers now support third-party containerized code running directly on the box, enabling operators to run custom control code on the router CPU. Second, we've seen a new generation of standardized control and config APIs begin to reach maturity. And this now has enabled the control code that operators do write to be uniform across vendors. Finally, we've seen over the past 2 decades that we've continuously gotten more and more on-router CPU resources, moving from a single core world to a multi-core, multi-gigahertz control dedicated set of CPUs. And taken together, this now enables operators to write operator-defined control applications that run entirely on the box, similar to how we run applications for server machines today. And further, we also have seen hardware advancements that support longer headers and more actions in the data plane. And this allows us to place longer header stacks on the packet, which we further double by a novel encoding technique that we present in the paper. And thus, a router can authoritatively dictate the path a packet takes via source routing without requiring consensus. Putting all of this together, we present our essential idea of decentralizing SDN. And we propose doing this by putting the operator-written control code directly onto the routers. Concretely, to do this, we replicate the central SDN, or CSDN's, control logic at every router in the network, which then allows us to get rid of the complex hardware and software infrastructure required to run today's SDN networks. And thus, in this design, every router runs a DSDN controller that floods its local state to enable everyone to learn a global network view, locally computes all paths using a traffic engineering algorithm, and then programs the end-to-end paths that originate at that router as a source route in the packets. Let's walk through an example together. So first, in this topology here, each node builds a node state update that contains local node state that the router reads via the standardized APIs mentioned before. This includes topology information and demand information. And then these updates are flooded, allowing each node to build a global view of the network. Then each node locally computes all end-to-end paths and encodes the paths that originate at that router as source routes that it adds to its forwarding table. Now, the fact that these are strict source routes that specify the exact set of links that the packet is going to take allows the path decision to be entirely consensus-free. as the ingress router authoritatively dictates the path that a packet takes. Then this end-to-end path is realized via strict source routing. And so when a packet arrives, it's through a lookup in the forwarding table, the strict source route is inserted into the header of the packet, and then the packet follows that path as specified in the header, as every router along the way forwards the packet along the links specified in the header. So in summary, moving from a centralized SDN world to a decentralized SDN world, we see that we remove the need for control infrastructure and restore the survivability lost through centralization that necessitated continuing to run traditional protocols by moving the control plane back onto the router. Now, let's take a step back and see if this achieved what we set out to do. Our goal was to maintain SDN's benefits, which were operator-defined code, running optimized T computations on a global view with the simplicity of consensus-free programming. And indeed, we managed to continue to run operator-defined code by running our own application containers on the router. We're able to run optimized TE on a global view by each router reading its local state via the previously mentioned APIs and disseminating it, allowing each router to have a global view. And we maintain the simplicity of consensus-free path selection through source routing, as the ingress router authoritatively decides the path that a packet takes. And at the same time, we also gain the benefits of decentralization, of fewer external dependencies because the control plane is running in-band, and the distributed survivability that comes with having no central point of failure. Now, turning to evaluation, we observe that the goal of both CSDN and DSDN is selecting and programming paths into the network. But observe that CSDN and DSDN both run the exact same TE algorithm that's specified by the operator. And so the final result is equivalent paths. Thus, our evaluation focuses on convergence behavior, or how paths are updated to become consistent with ground truth network state. And to evaluate this, we look at two things. One is the convergence time, or how long it takes to converge. And the other is the convergence impact, which measures how much or what impact the flows in the network experience during that convergence period. Taking a closer look at the convergence period, we see that it's made up of three components. Propagation, which is the period during which routers notify the controller about something that's occurred. Computation, which is the period of the controller computing a new solution. And programming, which is the period during which a controller reflects the changed paths, updated paths, back into the network hardware. And we see that these play out differently in CSDN and DSDN. So in CSDN, propagation happens entirely out of band, as each router notifies the central controller that something has occurred. Whereas in DSDN, this propagation happens in band, as each router floods updates about its local state. The computation period for CSDN happens entirely on the central controller, whereas in DSDN, the computation is replicated across each of the routers. Finally, in the programming phase, the CSDN controller talks to each router and establishes tunnels, whereas in DSDN, each DSDN controller programs the paths that originate at that router on that router directly locally. Now, in order to evaluate the convergence time, we implemented a production-grade DSDN controller and ran it on production equivalent routers in our test lab, feeding in the same production data our centralized controller receives today. And running and measuring this, we found that DSDN has a full 2 orders of magnitude faster convergence than CSDN. Now, this is because though the computation period is longer in DSDN, as the router has more limited resources than a data center where we can traditionally run an SDN controller job, because programming is entirely local and the controller lives on the router, we see a much quicker programming time. And likewise, because propagation happens entirely in-band, without traversing any external infrastructure, we also see a much faster propagation time, which taken together gives this 2 order of magnitude speed up in convergence. We also evaluated the impact during convergence by using a high fidelity simulator on production failure data over a 1,000-day simulation period, sampling failure events. And to measure this, we, for each failure event, at any given point in time, computed the blast radius, which was the percent of flows with more than 5% loss at a given time. And then for each event, computed the bad seconds, which we defined to be this integral of that blast radius during the convergence period. And in this way, giving us some metric to look at that appropriately penalizes larger impact or impact to more flows during a convergence period. And we find that across all priority classes, we see significantly lower impact during convergence. I encourage you to see the paper for more details. Now, additionally in the paper, we cover smarter on-router fast reroute techniques enabled by DSDN that can significantly decrease impact during link count reconvergence, novel techniques for strict source routing in label-constrained networks, and TE algorithm caching optimizations, and the on-router runtime scaling analysis. In summary, we've spent 30+ years trying to make decentralized protocols work more efficiently with more features. And then we've also spent 15 years now trying to make SDN-based networks work more reliably. In this work, we present DSDN, a new point in the design space made possible by recent router advancements that we show achieves the best of both worlds by decentralizing the SDN controller in a way that both maintains the simplicity of SDN, the benefits of SDN, but significantly simplifies the control plane infrastructure. And with that, thank you for your attention.